Now, this is sort of interesting, and we are going to generalize this now to 3 dimensions, because what this is saying is that the length of a segment AB divided by the distance of that segment to some point is preserved. Doesn't matter how far away I am. Okay? Okay. So what we are going to need for Gauss's law is this same concept, but in 3 dimensions. And so, for example, I could measure the height of that door, although that is easy, but the height is more complicated to measure, simply by standing some distance away, maybe half a block away or something. I can measure the distance from me to the base of the building. I can now put some stick in front of my eyes, measure put it so that it covers the building exactly. Okay, right? And then measure the distance from my eyes to that stick. And doing this trick, I can measure the height of the building, right? Okay. So then,
with any perspective, like
you have to be careful. But yeah, so you have to be careful.
even like camera shots and things like that.
No, well, if there is a little tilt, then no, not necessarily. No, I mean, this is true for parallel lines. If I now tilt the things, it was not going to work. Okay, I forgot to say that. So, for example, of course, it has to be exactly the same. It has to be similar triangles in this case, right? If you have a tilt, no, it's not going to work. Okay. So now there is a. Let me just first tell you about the concept. But so all of you know how you define a radian, right? A radian is, for example, the arc length divided by the radius, right? Okay. So if you have a small arc length on the circle, some that spans a little small radian angle, a small angle, then that arc length is going to be pretty much equal to the line that joins the last 2 points, correct? So if I define an angle in radians, always I can divide this length by the radius, of course. That's a full definition. But if my angle is tiny, then the distance from this point to that point will do a good job to define the radian, of course. Right? That's the way we do an integral anyways, right? So in other words, the arc length here is going to more and more coincide with the distance between the 2 points as I make the arc length very small. Okay, so then let's say, for example, this is very common in astronomy, that people define not radians, but so-called stereo radians. Okay, and this is for objects in 3 dimensions. So now you're not interested anymore on a length, but you are interested on an area. Why? Because you are interested, for example, in how much area a certain object in space covers. For example, the moon. Typically, of course, objects are relatively rounded, like the moon, the sun, but maybe there are some others are a little bit, strange shaped. But so whether you have a square or a circle, for example, you are interested in trying to give a number for how much it spans in space. Okay, how much how much of a moon I can cover with a quarter, a coin, that certain distance. And so clearly for us, the moon is going to be more difficult to cover than Mercury or Venus. Okay, even though those are really. Okay, so how do you think we extend the definition of a radian for the stereo radian, the so-called stereo radian, where the concept now is to describe, let's say, circles or little squares that are small. It's important that they are small, and that we are going to use in the construction of Gauss's law. So, in other words, okay, the reason I bring these 2 things together in the plane is because it doesn't really matter for this angle if it's 1 radian, to do the construction on a circle of 1 meter or in a circle of half a meter, I'm going to get the same result. Simply because of this construction here, as I reduce my dimensions by half, both the arc length and the radius are divided by a half in proportion. Okay, so that's why I brought this up. Because for the definition of the radian, it doesn't matter what circle I take. Any circle will do and everything is fine. Okay? Very good. So how would I do something similar if I want to talk about the moon or Venus or the sun or something, you know, or for example that clock that is sitting down there, I'm interested in giving some value for that from here, from where I'm looking. So we have two concepts here. What type of idea?
Three-dimensional. You put the left thing as kind of the arc length.
You put what?
You put the left geometrical concept, whatever that's called.
This one?
Yeah, that.
Okay.
As that whole thing has kind of a radius of.
Okay, very, very good. But if I have my object now, that clock over there, it's not a length anymore.
Yeah, it's not.
What is?
It's a three-dimensional.
But the way I see it, it looks like it doesn't look like a length. Does it look like a volume?
No, like a circle.
It's a circle. Exactly. Very, very good. Yeah. So I'll let you speak in a second. But so it doesn't look like a line, but it also doesn't look like a volume, because everything that I see with my eyes, with a telescope, etc., will look projected on a plane. So it's like you say. So it's going to be a surf, an area. Okay. So
the moon is also an area.
Yes.
But it's three-dimensional. Oh, you mean the surface, like the surface area? And you see
No, not the surface area. The way we see
is 2D.
The way we see is 2D, because you don't see so in the case of the moon, because we have the idea that is more spherical, then.
If you just look at
but if you look at a stone that is very regular, okay, it could look like a nice circle in one view, but it could be very messy in a different view. So clearly, what we see is the projection of the object on a plane that is perpendicular to the line of view, which is that's why I brought up that picture in 2 dimensions first. Okay, so we are getting close. So now we have our object is really a surface. We see a surface, okay, and now we need to construct another thing. So, for example, I have that clock far away. And now I can take a little circle here, and I just locate it so that that clock disappears at a distance of 5 centimeters from my eyes. Okay, so now I have a full construction similar to that one, but in 3 dimensions. I have a circle, a patch, a surface patch, far away, the object of interest. Closer, I have a little patch that I put there, okay? So the question is, how are those two things in proportion? With respect to the important quantities are the distances, okay? So I have the radius of the clock, the radius of the object that I use here, the distance from my eyes to the object, and the distance from my eyes to the clock. How are they related? Over there, they are related simply that their length, the ratio of the lengths are preserved. What about now? Huh?
The radius of one object is equal to the radius of is equal to the radius of the other distance. The radius of the plot over the distance between the plot is the same as the radius from the.
Perfect. So yeah, fine. That's correct. Yes.
The distance is equal to the change. Distance is equal to the change in area squared.
Also correct. Okay, so we're going to put those two things together. Those are two ways to say the same thing. Okay, so number one, let's start with the radius, because that's exactly what we said before. So if I look at the clock picture, okay, we don't need this anymore. If I try to make a picture of so there is an object far away, which let's say that's a circle. And then and closer somewhere we have another object that has the same shape. Okay, so one statement which is correct is that if I look at the lines on this plane, on the plane of the board. So for example, this thing is going to have a radius, and this thing also is going to have a radius, and then there's going to be, of course, a plane, which is the plane of the board, that contains the observation point, this radius and that radius, and now I can draw a line that goes through the centers. And using exactly the same argument that we use here, we obtain that the big distance and the big radius and the little radius and the small distance. So we have that R over D is equal to R over D. That's true because it's the same thing that we just stated before. Okay, but now you brought in another concept that is also useful, is to think about this in terms of areas. Okay, so if I wanted to bring up the areas in this problem, which is exactly what I want to do, I, for example, could consider a radius that is perpendicular to the one that we considered before. In other words, a radius that sticks out of the board, right? So I consider this radius. Now let me consider another one. And clearly, this is still going to be true for the other radius. Correct? So let me say it in another word. So this is one of the circles, okay? This page. It doesn't have to be a circle. It could be a rectangle anyways, okay? So if I consider the lines here, I could make that argument over there, and I get that the distance divided by some distance here is equal to the distance divided by the similar distance in the other object. But now I'm going to consider a line that is perpendicular to the first one. So first I consider these lines that are vertical. Now I'm going to consider a horizontal line, and I can write a similar construction. Right? And so if what I'm going to say here is not clear, I mean, we can prove it in 1 minute, but what I want to say is the following. This object here, this circle or rectangle, and this circle or rectangle smaller, have areas. If they are circles, of course they are going to have areas pi r squared. So let me call this big area and this small area. And so what can I say? It's very easy having this. What can I say between D, A, and A from here?
Square root of A over D is equal to the square root of A over D.
Okay, very good. Yeah, so I want to write that in a slightly different form, but perfect, yes. So what you are saying can be written in this form, that the R squared is going to give me the area, basically, up to constants. So A, that's the square of R, divided by D squared is equal to A divided by D squared. Correct? Okay, that's what I wanted to get at. Okay, so we are familiar with this type of similarities for lines, and now very easily we were able to go to similarities for areas. So now the areas, this basically is equivalent to saying that if I have an area, the way that the area looks drops like the square of the distance. Okay? So if I have an area that here looks like 1 meter squared, when I go, well, 1 meter squared at 1 meter, then when I looked at the same thing from 2 meters, then it will be 1/4 meter squared. That's what it says, etc., etc., etc. Okay?
So that's when we look at the moon? That's when we look at the moon from the Earth? That's the relationship?
Yes, so for example, if you want to find that's a different problem, of course, but I mean, because we don't know the distance, we do. But I mean, let's say that if you want to do an experiment at the street, you can actually cover the moon, you can measure the distance to the coin, but you don't know the distance to the moon in principle. So that's another problem, okay? But in principle, if you knew it, that's a way to compute the radius of the moon.
Yeah.
Okay?
But in that case, the radius would be bigger if the object
Yeah, that's the whole point. So for example here, okay, let's say that this is the moon and this is a coin. So what this is saying is that the area of the moon divided by the square of the distance to the moon is equal to the area of the coin divided by the square of the area to the coin. Okay? So actually, I'm not going to do it now because we have a lot of things to do really. I mean, but play yourself. This is really nice. These days the moon is very nice out, okay? The only thing I'm not sure if it's going to be cloudy today. But you can actually take a coin, uncover it, and measure the distance from the coin to your eyes. Okay, now you have the diameter of the coin, you have the area of the coin, and you have the distance to the coin. So look up in your freshman book of physics the distance to the moon and the radius of the moon and see that it works out. Right? Okay, all right, so we have that construction. Now we can actually get to think to Gauss's law. So what we want to prove is that the flux, this integral is called the flux, of the electric field over enclosed surface is equal to the charge inside. Now, in general, what's going to happen is this. In general, the electric field is going to be produced by a bunch of charges that are located somewhere in space. Maybe we know where some of them are, some of them we may not know where they are, but doesn't really matter. The electric field is produced by charges that are located somewhere in space. Okay? So we can do this symbolically, although some of them may be a continuum distribution, doesn't matter. But we have a bunch of charges, Q1, Q2, Q3, etc. And they are spread out throughout space. Okay, maybe there are a million of those charges. Now this surface has nothing to do with the charges. That statement is a general statement that should be true for any surface whatsoever that we consider. For example, we can consider a surface that includes all the charges, or we could have a surface that includes no charge at all. So this should be true in general. So in general, then the picture will look like this, where maybe some of the charges are outside and some of the charges are